part D.2, efficiency analysis of binary search. Yeah. Here you can see after our discussion in D.1, as soon as we determine how do we make comparison each round, right? Every time when we make a comparison, we base it on balancing principle, right? So just with that idea, strategy, simple step, we already get a binary search, right? Yeah. So this video, we just do the efficiency analysis. Yeah. So we're ready to go to the step, efficiency analysis step. Yeah. All right. So when we start, let us use a diagram to describe the binary search. At the same time, we work on the efficiency analysis. All right. Let us try to find the number of comparisons for the worst case. Now, 3 types of efficiencies: best case, worst case, average case. Now, best case, very trivial. You will see the best case is trivial. So one comparison, done. Yeah, that's the best case. Yeah. The worst case, we need to pay a little effort. Yeah. After that, the average case efficiency, another level of effort. You need to do, a few more steps. Yeah. All right. So let us start with the worst case analysis. Now, so let's go through the procedure another time, and this time, each step, we try to get a clear description on the data, on the given data. All right. So the whole line segment represents the given array. So we want to work on. Yeah. All right. So the given key, the black dot, given key, the first time we compare with the median element. Median. All right. And based on our basic method step, we drop 1/2 of the data after one comparison. Now, that is the elimination idea. So 1/2 of the current data will be dropped as a result of that comparison. All right, next round, the data size is reduced by 1/2. So we compare our current key with the current median another time and drop just 1/2 of the data, and so on. We'll keep doing until we reach the end, right? Eventually, we need to get the last step. The last step, we will see the result. All right. Here, let us do a simple chart to see what we have so far. From the chart, you can see the first comparison, the data size is reduced, and it is 1/2 of the original size. All right. Second comparison, the data size 1/4 of the original, and so on. Yeah. After K comparisons, the data size reduced to n over 2 to the kth of the data size, current data size. Then with this expression, we can do analysis. Yeah. Question: at what time should we stop splitting? Right? Eventually, we need to stop splitting. Yeah. So here, can you see the criteria that really tell us we should stop splitting? It does not make sense to do further splitting. Yeah. Can you identify that critical point? Yeah. All right, so here the criteria we can set like this. Yeah. after the last comparison, after the last, very last, that comparison, if we can detect or if we can calculate the data size less than 1, the data size less than 1, right? Yeah. So this expression less than 1. Do we need a further splitting? No. The data size less than 1, that means that small line segment can only cover one element in the array. Only one element in the array, that means that's the one. You either hit it, either equal, you hit that element, or miss it. Or if not equal, you can make conclusion the key cannot be found in the given array. You can already reach the final result. Yeah. So this is the criteria. Now, with this criteria, now we can use our formula to represent it. Yeah. So this is the formula. Yeah. Because the data size, this is the data size. Data size must be strictly less than 1. All right. Then the other side also important. This side, we double the final data size. So that means we rewind to the previous round comparison. The previous round. Yeah. Current round, data size already less than 1. The previous round, the data size should be greater or equal to 1. Yeah. Yeah. So we need this side. Otherwise, the K may not be the number of rounds may not be the minimum number of rounds, right? You may split too many times. We want to avoid splitting too many times, unnecessary times. So this upper bound tells us we do not do the redundant splitting. No redundant splitting. Just right. Our splitting just right. So this inequality gives us that condition, just the right condition. All right, next, the math simplification part. We want to get a relationship between the number of comparison K and the data size N, original data size N. Yeah. Let us just remove the common denominator first, so we get a simplified inequality. After that, then we take log base 2, try to get the K expression explicitly. Yeah, K. Yeah. Our goal, we want to find the K expression. So after we take a log base 2 operation, we're pretty close to get a K expression. Yeah, that is this one. Yeah, so you can see. Yeah, so this expression we almost there. Yeah, we almost there. Yeah. All right. So next we try to write a nice expression for the K number. The good expression. Okay. Yeah. Equal. Good expression, not inequality. Inequality is still not very precise, right? So we want to have a precise expression. Yeah. All right. Next, derive the worst case formula. All right. Yeah. So when we work on it, we start with this. Yeah. So here you can see that this formula is just a different way to write our previous inequality, right? Yeah, previous inequality. But this time, our main focus is at K. We want to get the range of K. The range of K, yeah. So K less than log base 2 of M plus 1. Yeah, so from here, from this part, we get K less than or equal to log base 2 of M plus 1. Yeah. This side, K greater than log base 2 of M. Yeah, pretty simple. Yeah. All right. From here, we can already get the K formula. Yeah. But I want to do a little more math work because I can get another formula. Yeah. This part we already have one formula, but I like to get another equivalent formula because there is something interesting I want to talk about. Yeah. All right. So this time, let us go back to the previous inequality. We have this inequality before, right? Think about it. We have it before. All right. So next, when we start from this inequality, let us do this step. n plus 1. Yeah, because if you just look at this side, this side, n strictly then 2 to the kth power. N strictly then. Yeah. Okay? Yeah. N strictly then 2 to the kth power. Then n plus 1. Yeah, we add 1 on top of n, right? Then n plus 1 should be less than or equal to 2 to the k. Because there is a possibility n plus 1 equals 2 to the k, right? There is a possibility. If there is a possibility, we should include that equal case in the inequality. All right. Why do that? Later you will see why I do this step, right? It looks like unnatural, but later you will see. I want to prove an important formula here. Yeah. All right. So from this inequality, let us take the log base 2 operation. So we will get this. Yeah. Definitely, when we take log base 2, we also use inequality from that side. Yeah. So we have upper bound, lower bound around k, but this time you can see this expression is different. Log base 2 of n plus 1. It's different. Yeah. All right. Yeah, it's different. All right. So now the conclusion time. Conclusion time. Two formulas. Two formulas. They look different, but they both give us the precise description, precise formula for the k number of comparisons. All right. The first one from this n plus 1 version. All right. Yeah. First, second, k max. Yeah. Max means the worst case, because worst case we need to do the maximum number of comparisons, right? So here I use k max. So that corresponds to the worst case. K max equals the ceiling function of, because k greater or equal to that log base 2 expression, and we know k is an integer. To log base 2 in general, it's not an integer. So for that reason, we take the ceiling function. That should be the smallest possible k number for the worst case. So that is our k max meaning. K max equals the ceiling function of log base 2 of n plus 1. That's the first formula. The second formula, k max equals 1 plus the floor function of log base 2 of n. That comes from this side. All right? The floor function. Floor function. Okay? Floor function of that 1 plus log base 2 of n, whole thing floor. 1 is an integer. We can move it out of the floor function, right? We have that property before, simple property. So we have the second expression. You can see these two expressions look different, but they are equal to the same thing, k max. What does it tell us? Same thing. What does it tell us? It tells us these two expressions must be equal. Must be equal. That means we prove it. So the extra work I did just now, the extra work, actually, it proves this formula. It proves this formula. And this formula, we used it before. Remember? Remember in the binary bits problem. In the binary bits problem, we used this formula. Yeah. We took it from Appendix A of our textbook. Yeah. We use it. In mathematical induction, we use it. Definitely, we cannot prove it at that time. Here, we have a chance to prove it. Although we don't have to, right? We don't have to prove it. But here, it is a good chance. If we just do a little more work, we can prove it. All right? Next, I want to do another useful thing here. All right. First, let us summarize a little bit. The best case, we know just the one comparison. The worst case, we just derived it, the formula. Yeah, so this formula, yeah, so you can use one of the two expressions. Yeah, let us take this default expression. Although we have another version, only when it is necessary, we use that one. Okay, yeah. So here, let us just use this by default. All right, yeah. Next, I want to ask you one question here. Now, average case efficiency. For the average case efficiency, can we just take the average of best case and the worst case, 1 plus parenthesis, the worst case expression, then the whole thing divided by 2? Is it the right way to calculate the average case? Yeah, because some students, they may like to use this simple way to calculate average case efficiency. Yeah, here I want to let you know the answer is wrong in general. In general case, it is wrong. Only in a very small, rare situation, it could be correct by chance. Okay, yeah, by nature, it's not correct. By chance, it could be correct. Okay, by nature, this way is dangerous. Dangerous. Yeah, don't assume you can do it all the time. All right, here, in order to convince you, in order to tell you why it is wrong, I want to work on one concrete example to let you see it. All right, yeah. What is the average case efficiency? Average case efficiency. Yeah. Here, let us use n equals 7 example. Then we can work on it step by step, and we can see all the details. The next slide, let us do it. Yeah. The last thing we will do for this video, this average case. All right. Here, let me just draw a diagram. Yeah. Our data, we have 7 elements sorted array. So let me draw these 7 elements in increasing order like this. Then we do standard binary search comparison. Level by level, from top to bottom. And we consider all the possibilities. Yeah. First, yeah. All right, yeah. So here, when we work on it, let us make a simple assumption first. We assume this V is in the array for simplicity. Yeah, because in this case, we can avoid some relatively complicated discussion. Yeah, because in general, in the real world, in the general situation, that may not be true. That assumption may not be true, because in general, we should assume that the probability that search key V appears in the array is P number, is a P number, where this P between 0 and 1, inclusive, even inclusive, right? Yeah, 0 possibility, it's possible. 1 possibility, one possibility, that is our assumption case. Yeah. Anyway, let us do the main part of the discussion. Yeah. So this part is not very important. We just aware of it. Yeah. All right. When we start the first level, the top level, we should compare it with the median. That's 4. Yeah. That's our first comparison. This is the comparison number. First comparison. All right. Then we go down to 1 level. When we go down the left branch of the tree, we should put 2 there. Yeah, based on our left median definition, right? So we should put 2 at the root of the left subtree. Yeah. And right subtree root, the median, still the median, node 6. Yeah. For these 2 nodes, we need 2 comparisons. Yeah. 2 comparisons. All right. Another level going down, so you can see 1 and 3. Node 1, node 3 under node 2. Yeah. 1 more level. All right. Similarly, node 5, node 7 under node 6. 1 more level. 3 comparisons. How about that? All right. Is it all the possible cases we covered? You can see this binary tree covers all the possible cases, right? Last step, we are ready to calculate average case efficiency. How to do it? We can write this formula, in this way. First, 1 comparison. How many nodes gives us 1 comparison? All right, so we can see. So the first one is the number of comparison. All right, number of comparison. How about that? I use C. Okay. The second node, number of node. How about that? Yeah. Number of nodes, number of comparisons, 1 times 1. The first term. Yeah. Second term, the number of comparison 2, the number of nodes also 2. Yeah, 2 times 2. Yeah. The third one, the number of comparisons 3, the number of nodes 4, right? Yeah. 1, 3, 5, 7. Yeah. Adding together all the terms and the denominator, total 7 cases. Now, then our answer is 17/7. See? 17/7. If you go back to check that one best case plus the worst case divided by 2, you will see different, right? Quite different. This is the right way to calculate the average case. Okay, all right. Hope you understand this way to do the calculation, because later in some exercise questions, so I will give you similar questions for you to work. So you need to know how to do the calculation. All right, so let me start our video D.2 right here.